Hello and welcome back to Calculus 2, section 8.3, Infinite Series. So as I mentioned the last time, we ignored the part on Infinite Series in sections 8.1 and 8.2, and we're going to take those parts now and consider those, and then take a look at two tests in addition. So last time we talked about sequences. And I said that the sequence is the ordered list of numbers. Ordering is done through a set of natural counting numbers, 0, 1, 2, 3, 4, 5, 6, and so on. We can get the explicit formula, we could get recursive formula, we can graph those, and then we can test them using the limit test, looking for convergence, divergence. We also had the vocabulary. But the important part is that sequence is a list of numbers. It's ordered, right? It's ordered list, not any list of numbers, but it's a list. You use commas. Now we define a series. Series is a sum of a sequence. Notation is symbol for sum, from let's say I goes from, or let's use n. N goes from 0 to infinity of an. So series is a sum of a sequence. So sequence an equal to, let's say, 3, 5, 7, 9, going on forever. You get the series come on, there we go. You get series for it, which is series an, and that will be 3 plus 5 plus 7 plus 9 plus dot dot dot. You see the same members between sequence and series. Same numbers, except sequence is a list, so it gets commas, and series is the sum, it gets pluses. Now, series can be finite, like the summation n goes from, I don't know, 3 to 7 of n squared, or infinite. Summation from 3 to infinity of n squared. Finite series always converge. That should be common sense, because you have to add a finite amount of numbers. So you have the list. In this case, we have 4 numbers. So we have 3 plus 4 plus 5 plus 6 plus 7, right? Actually 5. So you have 5 numbers here, and you add 5 numbers. So you will have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. You can work it out on the calculator and get a number at the end. So finite series always converge. You can always compute them. They are not interesting to consider at all, because there's nothing to learn there, right? It's the infinite one, right? Infinite ones are the ones that either converge or diverge. So the entire focus is on infinite series, because those can do one or the other, where the finite series always converge. They're not interesting, so therefore we don't look at those. Now, what does it mean for a series to converge? Well, it means that the sum is a finite number. So for series to converge to a number means that series has a finite sum. So you add infinitely many numbers and you get a quarter, or 2, or pi squared over 16. So you get a value. That's what it means to converge. Now, we can figure out a convergence of a series through a convergence of a sequence of partial sums. That is a labor-intensive work, but we can actually find whether the series converges or diverges that way as well. It's outlined in the book. I will show you what it means, but then, again, whether it's really not practical. Say you have infinite series from 0 to infinity of a n. All right? So to write this out, it's a0 plus a1 plus a2 plus a3 plus a4 plus a5 plus dot dot dot. What we do now is we obtain a sequence of partial sums. So sum 0 is just a0. Sum 1 is a0 plus a1. Sum 2 is a0 plus a1 plus a2. Sum 3 is a0 plus a1 plus a2 plus a3. So you see that all of these will actually produce some kind of a number. So I'll write S4 as well. A2, A3 plus A4. So you see that all of these are we call them partial sums because you use A0 and ignore the rest. Then you go A0 plus A1 and ignore the rest. So they're partial sums. You just take few terms, add them, and then ignore the infinity of other terms. Now notice that this creates a sequence S0, S1, S2, S3, and so on. So we are creating a sequence, and we'll call that sequence Sn. So we start with a series, and then we make the sequence of partial sums, and now that's a sequence. And now we know that we can take the limit as n goes to infinity of that sequence, which can have two outcomes, convergence or divergence. If it converges, then we can say that the series AN converges, and if it's divergent, we will say that series of AN diverges. Now, this is highly impractical to use. Highly impractical to use because you might have to find a lot of these partial sums to come up with a sequence, to push it together into some kind of term over here, and then do the limit. So it could be very, very unpleasant to do something like this. Now, what we do is instead we develop 10 tests. There are more. In Calc2 we learned 10, okay? So we develop 10 tests to use to test the series. So we have 1 for sequence, which is the limit test, and 10 for series for convergence and divergence. And we test them, right? So the first test that we are learning, the first out of 10, is geometric series test. So this is the one that it's probably easiest to recognize, or maybe second easiest, I don't know. So geometric series test. Now I did tell you this earlier. Make sure you memorize every test to the letter, and then the entire chapter becomes algebraic manipulations, if you know these things. And then in some case, a little bit of integration. Do what? Not even that. We'll see. So algebraic manipulations. Now let's go. Geometric series test. So we start if summation that goes from 0 to infinity of a r to the n, right? Has r in between -1 and 1. Then it is convergent. Otherwise, diverges. That's it. There are no calculations that you are going to do for these problems. You use your eyes and you look at the value of r, and if that value is between -1 and 1, series converges, and you are done. That's it. So if you don't memorize this theorem, you cannot do the problem. You cannot make this stuff up. So here are two examples. Summation of 3 to the n from 0 to infinity. So you look at this and you say, oh, r is equal to 3. 3 is bigger than 1, therefore divergence. And you walk away. That's it. Problem done. Or you have summation of 1/3 to the n from 0 to infinity. You will say 1/3, r equals 1/3, which is less than 1, right? It's between -1 and 1. Convergence. Done. You have to memorize the theorem. And if you memorize the theorem, you will be done with geometric series problem within 5 seconds. That's how long it takes you to write the stuff out. So you look at the value of r, and you just determine whether it's between -1 or 1 for convergence, or it's not. And end of story. Now we also have this value a. So that brings in another level of complexity. So you might have 3 times 1/5 to the n from 0 to infinity. And you would say, well, my r is 1/5, so I ignore that 3. Because that 3, the value a, is never mentioned in a theorem. As you can see, the entire theorem doesn't mention anything about a regarding convergence or divergence. It's just the value r. You look at r, right? You have to be able to locate r, and once you locate r, you are good to go, right, to say convergence or divergence. But now, there are more subtleties here. For instance, geometric series are one of the few where we can actually compute the sum if it converges. So now, this is where a is going to come in play. So next theorem says, if summation a r to the n from 0 to infinity is convergent, then the sum of the series is S equals a over 1 minus r. And this is where a comes to play.
Can I ask a question? Over here in the third point, the one that you mentioned about a, you said r equals 1/5 less than 3.
No, less than 1, sorry.
Oh, okay.
Yeah, I was supposed to say less than 1. The theorem is less than 1, not less than 3. Yeah, you're right. This was supposed to say less than 1. Because the theorem is between -1 and 1 is convergence. If it's equal to 1 or more, diverges. So now, if I take this problem, which stated 3 1/5 to the n, which was convergent, you have that A is equal to 3, R is equal to 1/5. We know it converges, right? We can compute the sum. And now summation is going to be S equals A, which is 3, divided by 1 minus 1/5, which is 15/4. So we can say that the series converges to 15/4, because 15/4 is the sum. When you add infinitely many numbers, you get 15/4. Right? That's what we have. So you add infinitely many numbers from here. What are those numbers that you are adding? What is this S? Right? What is this sum? It is 1/5 to the 0, which is 1, times 3, so 3 plus. 1/5 to the first power, which is 1/5 times 3, so plus 3/5. Plus 1/5 squared, which is 1/25, so 3/25. Plus 3/125, plus 3/625, plus 3 over, whatever is this, times 5. 3075, maybe? Or whatever it is. Plus dot, dot, dot. What is, guys, what is 5 to the 5? Anyone? No one?
3125.
3125. Yeah. Thank you. We have infinitely many numbers to add. They all add to 15/4 when you add infinitely many of these numbers. Now, 15/4 is 3 3/4, right? It's 375. And you can see that from here, because here's your 3 plus, right? And then you have 3/5, right? That's 0.6 plus, and then 3/25 is what? (0.12) plus 3 divided by 125 is 0.024 plus dot dot dot. So now 3.744 plus dot dot dot. You see that just by adding first 4 terms we got very close to 375. Now as you keep adding these terms to infinity, when you add all of the terms to infinity, they will add to 375 exactly. But we have the formula for that. We have a theorem that adds this quickly. And that is this formula here. You need to know your A, you need to know R, but you know those because you see them in the problem. You know what the A and R are from the problem. So you have to memorize the form of geometric series. And then when you memorize the form, the rest is not a problem. So if the geometric series is convergent, then the sum of the series is given by S equals A over 1 minus R. So you are memorizing the form of geometric series, and you are memorizing the sum of geometric series. This keeps sinking and dropping the stuff. It's just annoying. Stop doing that.
Professor?
Yes.
What's the value of 15/4? Is that like the limit, something you would approach but never get?
That's the sum. It is the limit of partial sums. If you make partial sums over here, you will see that the partial sums are approaching 3.75.
But it never does, and it never exceeds it.
Yeah, exactly. Well, in the limit is 375. You can't exceed it. Yeah. Right. Now, what we have here is, let's do another example. So summation, let's say 1 to infinity of 2 times 2/5 to the n. Converge, diverge, what is it? Converge. Because r is equal to 2/5, and that's less than 1, so we have a convergence. What does it converge to? Well, in this case, it's a very tricky question. Because your a is not 2. Now you're going, what the hell?
It would be 4.
It will be 4/5.
4/5.
Now,
Yeah.
you go and it's like, what? Well, let's observe this. And let's observe our definition. You see that? So those have to be the same. And then you get to use your formula. So now we have to perform procedure that it's called shifting the counter. Shifting the counter. Now, this procedure is important for your differential equation. Who's taking differential equations here? Anyone? Yeah. Well, who will take? Can't touch the ceiling. Let me see. That's the differential equations crew? All right. So, guys, this is going to be very important because when you differentiate series, counter moves by 1. When you differentiate one more time for the second derivative, it moves by 1 again. So when you hit the problems, see, this is the differential equation, and you see proposed solution is a series, and here it is, the first derivative, again erased, of course, the first derivative underneath, see counter starts at 1, and the second derivative starts at 2. When you plug everything in, the procedure I'm talking about is given in blue, which gives the term that we need. Now that's differential equations. For our case, I just need to make sure that you know that we need this. So this is not something that I'm doing just to annoy people. It is something that you will actually have to deal with as you go through your engineering courses later on. Because the counter and the exponent have to match. So what do we do here? We realize that this is n equals 1, because our counter is n, right? And we need that to be 0. So I subtract 1 on both sides. Oh my God, so. Subtract 1 on both sides to get n minus 1 equals 0. And now I can call this k. So what I got from here is that k is equal to n minus 1. That's the substitution. This counter could start at 7. Then it will be n minus 7 equals k. Right? You have to reset this back to 0. And from here, n equals k plus 1. Because once you substitute for the sum, the counter, you have to also substitute for the exponent. So now summation is k equals to 0 to infinity, 2, and you have your 2/5, but now, instead of n, you have k plus 1. So we are now able to match the counter. The definition says, the theorem says, k equals 0, as n equals 0, and our problem is k equals 0. So that matches. The problem is now that the power doesn't match, right? Because the definition here has 0 and n, and I have 0 and n plus 1. But luckily, we can use the basic algebraic idea, right? It's supposed to say times. Where I can break them apart as a multiplication. So this is where I get my extra 2/5. And now you see that the series turns into series 0 to infinity, 4/5 times 2/5 to the k. So from here I see that A is 4/5, R stays unchanged, 2/5, so convergence doesn't change obviously, only A changed, and now I can calculate the sum as 4/5 over 1 minus 2/5, multiply by 5 everywhere, it's 4, 5 minus 2, which is 4/3. So this is a tricky one. You have to pay attention at the counter. Counter must be 0, exponent must be n or k, whatever it is, doesn't matter. And you have to use the substitution to fix it if it doesn't match. So one more time, what happened? Counter started at 1. We can't have counter start at 1. We need it at 0. So I subtracted 1 to make it 0. Well, that created n minus 1 on the left, and I renamed that n minus 1 as k. Think of a u sub for integrals. So k is given as n minus 1, since I'm changing the counter from n to k, I have to change the exponent from n to k. So solve for n is k plus 1, and now I have the counter at 0, and n became k plus 1 exponent. Peel off the plus 1, which gives me 2/5, times 2, 4/5, and I have the new a, which is used in a calculation. And now we exhausted all of the problems. I noticed that this disappeared, so is there a way to, can I do this? Yes.
Since you mentioned this, what about I don't care about you, I care about that
Yeah.
in this situation?
There's no, yeah, well, that was the part where you are replacing the n with a k.
And then don't you replace it back?
No, because the form of the problem is the form of the problem is, I'm going to actually restart the program just to see if it's going to stop deleting. Yeah. Give me a second. Because it keeps deleting the stuff that I write, so. Yeah, see, it erased over here the 2/5 to the k. All right, so that should be it. I believe that this problem with the disappearing stuff, what I write, is the syncing with the cloud, and if I turn that off, I know with my luck I'm going to have the crash like this summer when I lost all those lectures, right? So I had to redo it. So we're done with geometric series, guys. That's it. The first thing you remember is the form and the R needs to be between -1 and 1. It's convergent. If it's less than -1 or more than 1 or 1, then it's divergent. Then you look at the R, determine convergent, divergent. If it's convergent, you can figure out the sum by adding these, by computing this. If the counter doesn't start at 0, you shift the counter and then figure out what the actual A is and compute the values. Yes?
Couldn't you get fancy so like the actual value of R is less than 1?
Yes.
So you didn't have to do -1?
Yes. So the notation that R, that R is between -1 and 1 can also be written as R is less than 1. So whatever makes you happy. One more test and we're done. And this one is actually, this one doesn't have a theorem, it's a procedure. It's called telescoping series. And your textbook doesn't make a big deal out of this. I believe they mentioned it as an example or maybe 2 examples. They don't give them the proper treatment as a, you know. So what we have is, so telescoping series is recognized as a difference between 2 sequences like this. Note that I'm not putting 0, 1, 2 because it doesn't matter. Geometric series are the only ones where they say you must start at 0. All others don't care. So geometric series, you must start at 0. This one, you can put whatever value you want over here. You can start at 0, 1, 7, whatever. So I will give you an example of telescoping series. Say you have summation of 1 over n minus 1 over n plus 2 from 1 to infinity. You can't start at 0 because if n was 0, 1 over n would be infinity, right? So we have to start with 1 in this case. I could have started at 10, doesn't matter. So, would this converge or diverge? Well, there is a procedure. We're going to write out few terms, and then we're going to write out few terms on the, what we call a tail end. We're going to try and make this finite, and then send it to infinity in a limit, actually. So let's see this little neat trick that we use. So when you have a subtraction of two sequences within a series, what you do is you write out few terms. So it's going to be 1 over 1 minus 1 over 3. Plus the next term is 1 over 2 minus 1 over 4. Plus 1 over 3 minus 1 over 5. Plus 1 over 4 plus 1 over 6 plus 1 over 5 plus 1 over 7 plus 1 over 6. Oh wait, these are minuses inside. 1/4 minus 1/6, 1/5 minus 1/7, 1/6 minus 1 over 8 plus, and I'll put dot dot dot. I have 6 terms there. So what I did is I computed, this one is n equals 1, this is n equals to 2, n equals to 3, n equals to 4, n equals to 5, n equals to 6. And I simply plug in what they are, right, for n and n. So when it's 1, 1 plus 2 is 3. And then for the next term, when n changes to 2, 2 plus 2 is 4, 3 plus 2 is 5, and so on. So we write out first few terms. And now, for the rest of the terms, I make the, plus, and now I'm going to use finite value k, because when it's finite we can deal with it, and then I'm going to send k to infinity. So instead of working 1 to infinity, I'm working to 1 to k. So, and then I will send that k to infinity. You remember your improper integrals? What you did? You have the integral 1 to infinity, and you said, okay, I'm going to do limit b goes to infinity, 1 to b. You're doing the same thing here. You are replacing infinity with k, and you send k to infinity. So what I'm going to do is I'm going to write this now as, let's say, 1 over k minus 6 minus 1 over k minus 4. They have to be 2 apart. Plus 1 over k minus 5 minus 1 over k minus 3. See, what I'm doing is I'm going all the way to the k value. 1 over, I'll show you the easier way later. K minus 4, 1 over k minus 2, plus 1 over k minus 3 minus k minus 1, plus 1 over k minus 2 minus 1 over k, plus 1 over k minus 1 minus 1 over k plus 1, plus 1, and the last term plus 1 over k minus 1 over k plus 2. You know you're done when this term is the same as the original series except as k's. I went way overboard with this, but we want to see a pattern. Let's see what we can do. Note that negative 1/3 and positive 1/3 cancel. Negative 1/4 and a positive 1/4 cancel. You have a negative 1/5 and positive 1/5. Negative 1 over 6 and positive 1 over 6. So I hope you see that this and this canceled both of their terms. Now, what's after 1 over 6 over here? 1 over 7, right? That one will cancel with this one. And then the next one after 1 over 7 is? That one will die as well. So as soon as you reach a first term that cancels both inside, you are done. The rest will all cancel. Look what survived. This and this survived. Everything else canceled to infinity. Now if you look from the tail end, you have exactly the same behavior. You see positive and negative. Positive and negative. These two. K minus 2. And K minus 4. We reached the one right there, looking from the tail end. That means that all others will cancel as well. So what is left? What's left is that 1 over 1 plus 1/2 plus the limit k goes to infinity of negative 1 over k plus 1 minus 1 over k plus 2. Those are the terms that are left, and we have to send those to infinity. But when you put 1 over infinity, what do we get? We get zeros. Yay! 3/2 converges to 3/2. Converges to 3/2. So the series 1 over n minus 1 over n plus 2 converges to 3/2 when you start from 1 to infinity. You have infinitely many of those. We started adding them up. This is what you would have to do all the way to infinity. Like this. I only did 6. You would have to do all of these guys all the way up to infinity, and when you add them all up, infinitely many of those, you would get 3/2. This series converges to 3/2. That's the sum. Converges to 3/2. But we have a clever way of doing it. Rather than sitting there for eternity computing all these numbers, we have this particular telescoping series test, right? Where you work out few of these, and they all go to infinity. Now, they all converge or diverge, right? Now, observe what I said before. As soon as you hit, when you start canceling, write first 5, 6 terms, right? Parentheses. As soon as you reach the first parenthesis that cancels both, everything else after that will cancel. Now, the trick for the bottom part is to start writing it actually backwards. I haven't done that. I wrote it forward and it looked confusing. So what I'm going to do now is I'm going to do one more example where I'm going to actually write the bottom part backwards, so it's going to be much easier to deal with it. Say you have summation of square root of n minus square root of n plus 1. You can start at 0 this time because square root of 0 is 0. Actually, let's start at 4 because we can. It doesn't really matter. Start at 4. So this is what I'm going to do. I'm going to write square root of 4 minus square root of 5 plus square root of 5 is the next number minus square root of 6 plus square root of 6 minus square root of 7 plus square root of 7 minus square root of 8 plus dot dot dot. I can stop because I already see that these guys cancel, these guys cancel, this one will cancel both of them, everything after that cancels. I don't need 5,000 terms. And now pay attention. The bottom part I'm going to start writing from the back. I know that the last term has to look exactly like this except with k's. So I write that one first. Square root of k minus square root of k plus 1. Plus. And now I just lower each one by 1. And I keep lowering by 1. So this one is k minus 1 plus root k. Right? When I take away 1 from here, it becomes k minus 1. When I take 1 away from here, it becomes root k. Then the term before this one is going to do the same thing. Yeah, it should be minus this one. Yes. So this one, take away 1, so it's k minus 2, minus, and then k minus 1. And the last over here I'm going to write, subtract 1 again, so k minus 3 minus k minus 2. So I started with the last term first because it looks the same as the original series except with k's. Remember, k is that finite value that we are going to send to infinity and see what the tail end of the series does. So now we write all of this and start canceling. Negative root 5, positive root 5, gone. Negative root 6, positive root 6, negative root 7, positive root 7, negative root 8 will cancel in there. Only root 4 survives. On the back end, It's completely symmetrical. All right? It goes backwards. These guys cancel, this one will die there. So what's left? What's left is 2 plus the limit of negative root k plus 1 as k goes to infinity. And this is exactly divergent. It's divergent. The limit gives us infinity. The square root of infinity is infinity, so divergent. So these problems are, it is a procedure. It is a procedure where you write the first 5 or 6 terms, and you will see very quickly the pattern, because it's all about the pattern. When these guys here are 1 apart, n plus 1, or n minus 1, when they are 1 apart, this one will be the first one that cancels both terms. When they're 2 apart, this one is the first one that cancels. When they're 3 apart, this one is the first. You will develop that sense when you do 10 homework examples. And for the exam, you will have no issues to determine exactly how many terms you need. If they are 2 apart, you will immediately know that you need first 3 terms, because the third term is the one that cancels both. And you see what survives in the first 2. I didn't know these things when I was taking the class for the first time. No one told me that. I went there and I worked out 6 terms, and then I made the algebraic mistake on one of them and nothing canceled. It was terrible. The key for this section is to memorize the theorems down to the letter, and then slowly peel off one by one. And when you get to the second part, start writing backwards. And as you can see, the last term here looks exactly the same as the series. 1 over n minus n plus 2. See? K plus 2. And then the next one that I'm writing is going to have minus 1. So k minus 1. Minus 1 over here is k plus 1. So now from here to here, take away 1. So k minus 1 is minus 2. And then k plus 1 minus 1 is k. So you write the last term the same, and you keep subtracting. Can I make this hard? No. Can I make this annoying? Yeah. So look at this one. Is this in our form that we love? No. Exactly. As soon as you unleash partial fraction decomposition, this will become our example 1 for telescoping series. So how about you perform a partial fraction decomposition, which is also, good introduction to the review, right? Because partial fraction decomposition is on the test in 2 days. So how about you crank partial fraction decomposition on this? You send me an email, make sure you don't get problem. Exactly. So do the partial fraction decomposition on this one, get the numbers, and hopefully you will get the first example. And you already know the answer for the first example, 3 halves. So we don't have to redo telescoping on it, but this conversion is important. Rebecca.
That's the part that's going to be on a test somewhere, but as referring to the first one, because it's a little bit different. The one over
Plus one now.
yeah,
Okay.
so it's a little bit different. It's kind of a combination of the last one and the first one together.
Yeah.
No. Should just be one.
That we stop until
I'm sorry?
we stop until we find the fraction that cancels in the same parentheses.
Yes. Well, you already have this done, right? This should be your example 1 that I did. It should be the same as example 1 I did.
Almost.
Or
It's slightly different, yeah.
Slightly?
If it was n in the parentheses n plus 2, then it would have been the exact same as the
Oh,
first
okay.
example. So,
all right.
So you like it?
What's new? Are you surprised?
Yes.
I will take that as a compliment. Yeah, second parenthesis should cancel. All right, so we have a plus b n plus a equals to 0n plus 1. So a plus b is 0, a is equal to 1, from where b must be negative 1 in order for them to add to 0, and this changes to 1 over n minus 1 over n plus 1. So we have 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 plus 1 over 4 minus 1 over 5. Then back end 1 over k minus 1 over k plus 1. Half kills, third kills, this dies. On the back end, then done. What's left is 1 plus the limit of negative 1 over k plus 1 as k goes to infinity, which is 1 plus 0, which is 1, and the entire series converges at 1. So when you add infinitely many of these terms, they all add to 1. What happened?
No, instead of x plus 1, I got n negative 1, n minus 1.
Oh, we probably didn't write it because it's n plus 1. You have to keep the same, n plus 1, n plus 1. You just copied it wrong, probably. For partial fraction decomposition. And that's it. Hope you're not disappointed, guys, but that's all. And we got to review a little bit of partial fraction decomposition. All right, so let's reset for the review.